In Unit 5, we are going to be talking about chemical kinetics and all the variations of what that means. We have focused mainly on stoichiometry, some energy things, but rate is a big factor. Another characteristic of chemical kinetics to consider is called spontaneity, which refers to the inherent tendency for the process to occur. A lot of people, when they hear spontaneity or something spontaneous, they think means it's really fast. That is not the case. Spontaneity doesn't have to do anything with speed. You can have spontaneous reactions that are very slow. It just means that they are going to happen. They are going to proceed as predicted. Some spontaneous reactions can happen very slowly, like for example, rusting. When iron turns to iron oxide, that rust is a very slow reaction. We know it's going to happen, like for your car, for example, if you don't take care of it, but it happens very slowly, so a lot of times it doesn't even look like it's reacting to us, to our eyes. So in order for chemical reactions to be useful in industry, we must also understand the factors that govern the rate of reactions. This area of chemistry is our definition for chemical kinetics. One main goal of chemical kinetics is to understand the steps by which a reaction takes place. This series of steps is called a reaction mechanism. In this unit, we're going to first look at rate laws, how a rate can be affected, reaction mechanisms that are possibilities, and then simple models for those chemical reactions. This is taken out of your textbook, pages 555 and 554. But if we had a reaction of nitrogen dioxide and it decomposes into nitrogen monoxide and oxygen gas, the pictures at the bottom are a representation over time in a sample of what it would look like, and then you're given some data. At time equals 0, those are called initial conditions. So when it's initially, right when it starts, what do you have? Okay, so initially we only have reactant, NO2, but no nitrogen monoxide and no oxygen gas initially, which is shown in the picture. A. But as time progresses, the concentration of the reactant goes down while the concentration of the products goes up. Okay, we're going to get into something called equilibrium soon, but do you notice how we don't completely use up all of the reactant? It just goes smaller and smaller and smaller. But I think the reason why the dotted lines are around these is to show you that, oh, these products were made from those two reactants. I really don't know any other reason for those. But that just is a way to show you how a reaction progresses over time. And then this also is on the next page in your notes, and it's a graphical representation of concentration versus time, where the green line is the reactant, so that starts up at the concentration that was listed in the table, and the two products both have concentrations of 0 at time equals 0. But as time progresses, the reactant goes lower in concentration, and the two products gain concentration. So that's just another way to see it. Chemical kinetics deals with the speed at which these changes occur. So the speed or rate of a process is defined in the change in a given quantity over a specific period of time. The rate at which you travel in your car is another speed or rate, like miles per hour kind of thing, where you have amount over time. For chemical reactions, the quantity that changes will usually be the amount or concentration of a reactant or a product, and that's what we're going to measure. So the chemical reaction rate is defined as the change in concentration of a reactant or product per unit time. So it's like slope formula. You could take the two concentrations, remember brackets mean concentration, specifically for molarity or moles per liter, and the triangle, the delta, stands for change in. So we have the change in concentration over the change in time. Time can be seconds, it could be minutes, it could be years. It just depends on the situation. The change, when we calculate it, can be positive or negative. If it's positive, it increases. If it's negative, it decreases. And it will change the rate of reaction. So with all of this, we have what's called the collision theory model. We are going to be looking at this more later on this unit. But according to collision theory, atoms and ions and molecules react when they collide with each other, but only if they have enough kinetic energy. If they don't have enough energy, they will just bounce apart unchanged when they do collide. So there are a couple of factors that weigh into collision theory. The picture on the screen is not as nice as the picture in your notes, but they have to have enough energy, so that's what the top picture is showing. If they're not moving fast enough, they don't have enough energy, so they will not change. And they have to be oriented properly. They have to be arranged in a way that when the parts of the molecules hit each other, then a chemical reaction can occur. So if they're not arranged properly, there won't be a reaction. So the two main things that we need to know is that they have enough energy and that they're oriented properly in order for them to collide and react. We have lots of different things that will change the rate of a reaction. Some reactions, like I said, are naturally fast and some are naturally slow. But you might need to modify that sometimes. So we can influence the rate of reaction by changing concentrations, temperature, surface area, catalysts, and other environmental factors. First of all, temperature. Usually, raising the temperature of something will speed it up a reaction because you're giving it more energy, you're giving it kinetic energy, and lowering the temperature will slow it down. So this is just, remember from when we talked about gases previously this year, that when you have more movement, there's a higher frequency of collisions, so there's more likely a chance that it's going to collide and react. So the products will form faster. When you have more movement, we say that the particles are able to slip over what's called the activation energy barrier. We're going to talk about that more later on. What does that barrier actually look like? It's a number value. Changing the concentration will change the reaction rate. So the numbers of particles that are there in your sample will have a say on how fast it reacts. The more particles you have, the increased concentration, and if you have more particles, there's just more chances that they can react with each other by colliding. So that would increase if you increase the particles, and that would increase the reaction rate. Particle size, if you have a bigger particle versus a smaller particle, that will change it. Surface area is what it has to do with. So the smaller the size of the particle, the more surface area it has, and more surface area allows for more reactions. If you are not necessarily able to, or sometimes you can, but you can dissolve the reactant, we do a lot of solution chemistry. We dissolve it in water, and that's because the particles are separated and more accessible for other reactants to actually react. But if you can't dissolve it, then you can also grind it into a fine powder to increase surface area, or just cut it up. Catalysts, we've heard of catalysts before. We use catalysts when maybe increasing the temperature is not the best way to go about it, or maybe we don't want to increase particle size, or we can't increase the particle size. So the catalyst is a substance that will increase the rate of the reaction, but is not used up. So it's not actually put in as a reactant or product, it's just there to help. Okay? Catalysts permit reactions to proceed along a lower energy path, which allows for the reaction to need less activation energy. So if you look at this graph, this is our energy path graph, okay? The solid line is what the natural, without the catalyst, energy path would be. And then do you notice how the dotted line shows with the catalyst and the peak is a lot shorter? So the peak height from Y, which stands for products, up to that top of the peak is the EA. That is the activation energy. And so it takes less energy with a catalyst to change from reactants to products. So that's what, in a nutshell, what catalysts do. Since they are not consumed in a reaction, the catalyst might be written as above the arrow, as you see here. Another catalyst that you might see sometimes, it might just say heat, and they're writing it like a catalyst. Or platinum is used for hydrogen fuel cells to be a catalyst there, so that you might see something like that. So catalysts do not appear as a reactant or product because they are not actually consumed. They are written above an arrow sometimes to show that they are different.